All right, here's a quick review of related rates. For any related rates problem, you'll be faced with a paragraph. Read it and carefully identify variables that are given and variables that are asked for. Go ahead and label them. Label them in your picture, and you're ready for step 2. From your picture, there should be some equation that you need to write. Your picture might be a right triangle, in which case you might do a squared plus b squared equals c squared. Or your picture might be a right triangle, in which case the equation you write will be a tangent ratio or a sine ratio. Your picture might be a sphere, and the problem might talk about surface area. So your equation might be the formula for the surface area of a sphere, or maybe the volume. But there's going to be an equation to write. Once you've written that equation, differentiate with respect to t. You're probably going to need to use the chain rule here because your variables in the equation will be functions of t, so we'll differentiate implicitly. Once you've differentiated implicitly, you'll plug in all the values that were given in the problem, and what remains should be what they were asking you for. All right, let's look at a few examples. For the stone in the pond problem, all we had to draw was a radius. The circle's already drawn for us. They told us that the radius's rate of change is 1, and they asked for how fast the area is changing when the radius was 4. So the equation is just the equation for a circle. Keep in mind that your variables here are functions of time. So when you differentiate with respect to time, we'll have dA dt on the left, and we'll have to use the chain rule on the right. Power rule, 2 times pi r to the 1 power times the derivative of the inside, dr dt. Once you've done that, you're pretty much done. They gave us the radius of 4. They gave us the dr dt of 1. And there we have it. The area is growing at 8 pi square feet per second. Next example will be a little more difficult. All right, in this example, we have a camera tracking a launching rocket. So that picture is pretty easy to make. It's 2,000 feet away, and the rocket's height is 50 times the square of the number of seconds. Find how fast the camera angle of elevation is changing when t is 10. So in this problem, we had an expression for the height. We knew the distance away was 2,000, so with respect to theta, that's the opposite and adjacent side, or a tangent ratio. So tangent of theta is 50t squared over 2,000. We can reduce that. All right, so that was easy. Now we just take the derivative with respect to t, and we get secant squared of theta times d theta dt, and the derivative of t squared over 40 with respect to t is just t over 20. All right, so like before, when we plug in information that we know, we should be able to find what they're asking for, d theta dt. We know that t is 10, but we don't know what secant squared is. So at that point, recognize that we should be able to figure out what it is. Go back to your picture. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse. So secant will be hypotenuse over adjacent. That means we have to find the hypotenuse. So using the Pythagorean theorem, hypotenuse is the square root of 29 million. So cosine of theta is 2,000 over the square root of 29 million. Secant is 1 over cosine, so secant squared is 1 over cosine squared. So to get rid of 1 over cosine squared, we'll multiply both sides times cosine squared. And cosine squared is 4 million over 29 million, or just 4/29. So we can plug that in. 10/20 times 4/29. Write down the units. The camera angle's elevation is increasing at a rate of 2/29 radians per second, which is about 3 3 or 4 degrees per second when the rocket's been launching for 10 seconds. So in that last example, we needed to use a trig ratio. In this example, we're going to have to use something else, but still geometry related. All right, we have this triangular prism trough. We label its length of 12 feet, the 3 feet width of that triangular side, the 4 foot altitude of that isosceles triangle, and the 2 cubic feet per minute is how the volume is changing. And they ask how fast is the water rising. So they gave us a depth of 1, but don't include this in your picture. When you make your picture, there will be some things that are changing in related rates problems. And for those changing quantities, your picture should represent them with variables. Don't put the constant 1 here. It's not a constant. This water level is changing. So that variable can be h. This is the other variable that's changing. And notice that we have a little triangle, which is similar to the original triangle. So volume of a prism is the area of the base times its height. So the area of the triangle times 12. And that reduces to 6bh. At this stage, if you try doing step 3, the implicit differentiation, you're going to run into a problem. B is a variable, it's changing with respect to time, and so is h, and so is v. So we would get dv dt equals 6 times the derivative with respect to t of the product of these functions. So we'd have to do db dt times h plus dh dt times b. But we don't know db dh. So before we go any further, we want to do a substitution so that we only have the variable h on the right. And that's where the similar triangles comes in handy. Similar triangles have proportional sides, so corresponding ratios will be equal. 3 to 4 will be equal to b to h. And from that proportion, we can see that b is 3/4 h. And when we substitute that in, now we have our function just in terms of v and h. So, step 3, the derivative with respect to t, we get dv dt equals 2 times 9/2, h to the 1 power times dh dt. And at this stage, we have been given everything we need. Volume is being pumped in, changing at 2 cubic feet per minute. The height of the water column was 1 foot at that point. And so dh dt is 2/9 feet per minute. All right, the next example will be a follow-up where we need to pay close attention to the units, and that will be it. Same problem, but we don't know how fast the water is coming in, so let me cross that off. Water is pumped in at a rate that we don't know. That's actually the ask. All right, so we don't know how fast the water is coming in, but we know that it's rising at 1.8 inches per minute. So the issue with this problem is we have dimensions in terms of feet. Right? The trough was 12 feet long and 3 feet across. So when they talk about the dh dt in inches per minute, we should convert that to feet per minute. So 1.8 inches is the same thing as 3/20 of a foot. That's pretty much it. We can use the same equation. dv dt equals 2 times 9/2, or 9h to the first power times dh dt. We know that the height in this problem is 2 feet. We know that dh dt is 1.8 inches per minute, which is 3/20 feet per minute. So you multiply that out. The volume is changing at a rate of 2.7 cubic feet per minute. That's as far as we got, and then the rest of the class time we use for practice.